Hey guys, this is JSer. How's everything going? In today's video, I'm going to take a look at 1473 Painthouse 3. Actually, I did this in today's live contest, but I didn't make it. I tried the backtracking solution, and it cost too much time. And of course, I met TLE, and it actually worked, but it's very complicated, and I didn't made it to avoid the duplicate calculations. So after that, I did some investigation and take a look at the discussion that other people are talking about. So I finally understood the key point of this problem. So I made this video. Hope it helps. To be clear, this is not. I didn't came up with this solution. Yeah, let's just begin. So there's a row of M houses in a small city. Each house must be painted with one of the N colors, labeled from 1 to N, with one base. Some houses that has been painted last summer should not be painted again. A neighborhood is a maximal group of continuous houses that are painted with the same color. For example, the houses like this contains 5 neighborhoods, 1, 2, 2, 3, 3, 2, 1, 1. So each neighborhood should have the houses painted with the same color. Now we're given an array houses, an n by n matrix cost, and an integer target, where houses I is the color of houses I. 0 means not painted yet. Cost ij is cost of paint house I with the color j plus 1, because color is 1 base. Okay, so I need to return the minimum cost of painting all the remaining houses in such a way that they are exactly target neighborhoods. If possible, not possible, return -1. Suppose we have 5 houses, none of them are painted. Now we have the cost table. Like this means that the first house costs 1 to paint color 1, costs 10 to paint color 2, the same for the rest. Now we need to paint all 5 houses with 3 neighborhoods. So the best approach is 1, 2, 2, 1, 1, which are exactly 3 neighborhoods. 1, 2, 3. Now let's see the cost. Because the first house is to be painted with 1, so cost 1. The second one costs 1. The third one costs 1. The fourth one costs 1. And the last one costs 5. So totally 9. Okay. So for this kind of problem, there's nothing to start with at the beginning, right? It just seems like so I didn't even know where to start, so I just start backtracking, which is not a good idea. The best way to solve problems, I think, is to recursion, right? For most problems, yeah, I forgot that. The best is to do recursion, and then try to improve it with dynamic programming or memoization or anything. So for this one, let's just take a look at the basic examples. For example, we have 5 houses need to paint, and just the first example. Now, for the first house, what is going to be painted? Well, there are 2 possibilities. Let's see what happens if we paint 1. If we paint 1, it means there's already a neighborhood, right? So for the next one, let's say if it is, I don't know where to paint, something like this, right? So we need to actually to create create target -1 neighborhood, right? Neighborhood from index equals 1, right? Yeah, but let's take a look at deeper. Actually, this one, right? There's a problem here. If it is 1, if you choose to paint it as 1, it actually doesn't create a new neighborhood, right? If this is the case, we actually need to create the target -1 neighborhood from index +2. Okay, index equals 2, right? Because there's only 1 neighborhood here. Well, if this one is choose 2, then actually we need to choose target, create target -2 neighborhood, right? From. So this is a basic recursion relationship. So actually, let's see if if this subproblem looks like a recursion, right? We just create target 1 neighborhood from index 1, which is the same similar to create target neighborhood from index at 0. But the previous color actually matters here. If the previous one is 1, when we are starting 1, we don't add 1 neighborhood. If the previous one is not 1, well, this add neighborhood. So actually, if we create a paint method, the first one, the steps which are gonna be used in the recursion should have I think it should have 3 parameters, which one is the start index. Let's say house index. The next one is prev counters, right? Prev house. This is prev counter, and then the target. I say it's neighborhood. Okay. This is the recursion with the paint method. So at last we could do what? We could do, the problem should be, we should paint from house 0 with prev counter, because no matter what we choose for the 0 index, we always create a new neighborhood. So we prev set to -1. This no cutter will be -1. So yeah, and the target, we just pass in target. Now let's just try to do our recursion. Well, because the house might have origin cutters, like it might be not 0, it might be something different than the previous cutter. So let's create some if clause here. Okay, the const origin cutter, it should be house index, right? Cool. Now, if origin cutter is 0, it means we could paint any cutter, or origin cutter is already painted, but it is prev cutter, or if it is not the previous cutter. So these are 3 cases, right? Cool. And for each cases, we need to get the minimum, right? So mean cost. Okay. So if it is 0. If it is 0, what we do? Well, if it is 0, we just we could paint anyone, right? We could paint any cutter. So we loop through the cutter. We paint it. If we paint, we need to add the cost, right? Add the cost from the cost table. And what you do, if we paint with the cutter, we need to actually, like here, if we paint 1, we need to paint, just continue our painting, right? So we paint next one. So the cost. So for each of these for each of these possible cutters, actually we get a possible optimal result. So we need to update the minimum cost among all of the past solutions. So we create a minimum would be infinity. So the cost would be, okay. So the possible mean cost should be what? Should be paint, right? Paint the next one. Paint the next one is house index +1. Prev cutter is our cutter, which is I, and the neighborhood. So this is a tricky part. If the next cutter, if this is gonna be paint, paint, right? If the current cutter is the same as previous one, then the neighborhood doesn't change, right? So if I, which we're gonna paint, is equal to the previous one, then it is within the same neighborhood. So neighborhood. If not, we have a different neighborhood, so we -1. And then we need to add the cost, right? So cost house index cutter is I, so I -1. So this would be possible mean cost. Yeah, this is one possible mean cost. when we paint this house to I with the color I, and we update it, math mean possible mean cost. So this is the how we handle it when it is not painted yet. So we do the similar for if it is already painted and it is previous color. Well, it's simple, right? So for this case, we don't add neighborhood, so we don't need to -1. So we just say main equals, okay, we just create another, okay, we just update it, main equals math main. It should be paint, right? We paint next one, house index +1. The previous color is the origin color, right? It's origin color. And the neighborhood, we don't need to change it because it's the same in the same neighborhood. Okay, so it's done. And if it is a different color than the previous color, what we do? Well, we just say main math main. We paint the next one. Origin color is the, we use origin color here, but the like here it already is a different neighborhood. So for the next one we need to -1. Cool. So this is it, and we just return the minimum, right? So when will these recursion end? Well, it should end when the house index is all the houses are painted. So if houses index equals to m, we need to return. When we go to when all the houses is painted, neighborhood should be equal to 0, right? So if there's no neighborhood we need to create, if it equals to 0, then we return 0, right? Cost is 0. If not, there's no more houses to paint, so it's infinity, right? Cool. So this is it. I think it should work. Let's try to review our code before we submit our code. So we create a paint function. This paint accepts house index, so which houses to paint, and previous color, and the neighbors. Target the how many neighborhoods you want to create. Well, if the houses, all the houses are painted and the neighborhoods, we don't need to create any neighborhood. We return 0 or infinity. It means impossible, right? And we get the current color. If it is 0, which means we could paint any color. So we paint it next one. We try to paint the next one. Previous color is I. If this color is the same as previous one, then neighborhood doesn't change. If not, we -1 and plus the cost we pay, right? Yeah, so we update the minimum. And then if the color is already painted, if it is the same as previous one, then we just continue paint the next one with the neighborhood we want to create. And if it is different, then the current house create a new neighborhood, and we we change it to -1. So we return minimum. Yeah, this should work. Let's run the code. Yeah, but actually, we said if it's impossible, we need to return -1. So we need to check if it is infinity or not. Cool, we submit. Look, I have tried a lot. It's always meets the time limit exceeded. It's hard. So yeah, of course, we got time limit exceeded. Well, it's very it's not that easy, but we might be led to the conclusion that if we say we need to paint the houses in the middle, like index to 2 with previous color with 1 and neighborhoods with 2, we need to find the minimum cost for a sub problem like this, right? But the previous color, and the previous neighborhoods for the houses before this index, actually they will have many possible combinations, right? So might not be one possible combinations, which leads to our request, our call of paint at specific house index, specific previous color, specific neighborhood. So there's a lot of duplicate calls to paint, right? So that leads to the memoization. Sadly, I didn't come up with this approach at the live contest. So this is very straightforward, which is a cache approach. We just say cache. We create a new map. Well, we create a key. If it is already checked, then we just return the result. And then we need to set the cache, right? Cool. Let's run the code. It should work, and we submit. Yeah, we are accepted. So this is approach of memoization. Well, you see, we only add the memoization, and it just it is accepted, and so it helped reduce a lot of time. So what's the time and space complexity of our approach here? For time. Hey guys, after I draw some graphs on my notepad, finally I think I got to understand what time complexity for this problem is. Let's try to allow me to demonstrate what I have done. So to analyze the time complexity of a recursion, the better thing would better try to understand the call tree, right? So let's see, for the first time, the call tree of paint. Okay, the first call of paint should be paint 0 minus 1 k, right? Now this is target, which is use t. This is the first call, and this call actually will trigger the following calls. Actually, it will trigger 1 k minus 1, and then 1 2 k minus 1, which means for the next index, right? Okay, so actually we could remove the depth here. So you see, it's the same. So this previous one is 2 k minus 1, right? And then previous one is n k minus 1. So these will in turn will trigger what? Will trigger, you see, it will trigger the previous one is for the case here. This will trigger because previous one is 1. Now for this index 2, if this 1, then k minus 1 doesn't change, right? So it will trigger 1 k minus, okay, I'll write it down for better understanding. So 1 1 1. This is dot 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 dot. Okay, that's over 2. If the previous one is 1, no, we will, because previous one is 1, and then we'll call this with minus 1, right? And then we will call 2. This is for the case here. It means for the first number, the previous one is minus 1, but actually it could be anyone, right? Okay. Now for the case here, it means the previous one is 1. Actually, for 2, it could be anyone, right? It could be anyone. So if it is previous 1, then it is the same as previous one. So it doesn't create a new neighborhood. So now here should be a 2 2, which meant minus 2 k minus 2, right? Because For two, this is for the first index actually, for the index of is 1. But now, and because previous one is 2, then for the comparing to the previous one is -1. Oh no, for 1, it's different. So it should be k minus 2, right? So it should be 2n k minus 2. This will be all continuing, and so for here it will be 2, 1 k minus 2, dot 2 k minus 2, dot, 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 2n k minus 1. Well, let's just review it one more time. This is for remains for the first yes, for the first position. The previous one is -1, right? When we code it, to actually for the position here, it might be 1, 2, n, right? That is for the next index. That's but for the next index, this is the previous possibility. So for the here, it is the possibilities for here, right? But the previous is for 1, means for 1. Yeah, so if it is first 1, it doesn't change the neighborhood, okay? So for the case here is 2, then we update here. So for the last case is 1 for n. If the first one is n, then the case, all the possibilities for index 1, if it is still n, then the neighborhood doesn't change, right? You see? So you see for index 2, actually there will be how many? There will be actually for each of these n cases there will be n, right? This is without memoization, I say. So for a layer here, it should be n, but here it will be called n to the power of 2. So each of the possibilities will generate new possibilities. So if we do nothing without memoization, it actually will be leads to okay, for 1 plus n to the power of 2 to the power of m, actually. So it's I think it should be m. There's a case that k, right? If k is smaller, this will actually be smaller than this. Let's say the k is big enough, so we will always travel for our solution here. We'll always traverse to the n, handle the last index. So I think it should be a reasonable, like a upper bound. Now this is the without memoization. If we with memoization, what will happen? You see, for the case of 2, we see that for the combination of these, actually there will be for the second there will be n possibilities, right? 1 to n, and here the possibility will be 2. The next one will be 3, right? So if we do the memoization, the tree will stop at no. A lot of the calculations could be avoided by just getting the result from the cache, which means for the first layer it will call with 1. For the second one it should be n, right? So it should be n times 1. And next one is n times 2, right? Because you see for the possibilities will be n here or 2 possibilities, k minus 1 or k minus 2. Okay, so the third one it should be n plus 3 times 3, right? So dot dot dot. So last, which is n times m, with the assumption that k is big enough, we can have this. Actually, it will end shorter at k, right? Actually, so if we sum them up, it will actually create a time complexity with n times m squared. Yeah, so actually this is our time complexity. If we fail, if we terminate it without going to last index, actually we can see that the length k sliding window, like a sliding window k, just moving to the n m. So actually, it would be, I think it would be reasonable to think it should be n times m times k, right? Yeah, suppose this should be like a k, length k, interval, k intervals like overlapping with each other. So yeah, I think we could reasonably think if it's a O M K. So for the space, well, for each layer it's different. So actually, this will just be the same O M K. Yeah, upper bound will be m to the square. Actually, our solution here, it should be n m to the square because we were going to the last index, right? We didn't think of the neighborhoods being minus. So we should, if we're gonna improve it, okay, this is a count. I counted I count the call of paint to validate my assumption. So this is done. Yeah, is already done. So this is a result, time and space complexity. This is actually should be m squared. How could we improve to m and k? We should stop when neighborhood is minus, right? And negative, right? So it's negative, it's impossible. So if this, okay. Yeah, if neighborhood is smaller than 0, we return infinity. Yeah, so that's by these if clause, we improved the time complexity from n m squared to n m k. Yeah, I think so. Let's try to run our code. It should be a little faster. Yeah, okay, so that's all for this one. The time complexity cost me a little time. Hope it helps. See you next time. Bye-bye.